You're live.
We did it. Or did we?
Hello.
we require some external confirmation, and then I know. But then, I guess you've been running the stream live the entire time, Pamela, so you know that it's working.
Yes, I do. It is working.
Yeah, yeah. We don't have a fancy introduction for this, though, do we, yet? It's just
not like
Astronomy
Astronomy Cast, yeah.
Yeah, like Astronomy Cast does.
Yeah.
If you make a fancy introduction, I'll play a fancy introduction. We do not have a fancy introduction, though.
So if people are interested, I have been interviewing each member of the team from Universe Today on our Patreon feed, and we've made them all public. So I've got an interview with Nancy Graziano, an interview with Nancy Atkinson, Anton Posnikoff, who's our new producer. I just interviewed Andy Thomaswick. Dave, you're in my gun sights at some point.
Yes, that hasn't occurred yet. Yeah, I'm here all summer. So
Yep. So we'll interview you and Alan Boyle and Matt. So if anyone's interested in just sort of behind the scenes in being a science writer, science communicator, I think you'll find these interviews quite fascinating. They're really interesting, sort of the way we roll at Universe Today, but also how they approach stories and each one of their strengths and weaknesses, and how much material they write and how they go about getting a story, and how they make sure that they're not a press release word scrambler. You know what I mean? It's interesting. So I think people might really find this interesting. And so the plan is to go through the entire team. So we will have an interview with each person. It's only audio. But yeah, we'll have an interview with each person on the team, and just so you can learn about what it's like to be a science journalist, especially if, I think it's interesting for people who are either on the show or interested in becoming a science communicator, a science journalist. Nancy has probably written 6,000 articles for Universe Today.
She used to edit way back when. So.
Yeah, and she used to be our senior editor. So she was the one who was picking stories, editing everybody's stories, and contributing an enormous amount to she's written multiple books, and just got book offers handed to her. So just like Dave.
2 books. Working on third, maybe.
Yeah, exactly. Yeah. So it's very interesting. So another reminder, and I'll mention this in the show, but this is the final episode before we go on hiatus. So I don't know what to tell you. I feel like I've warned you. We've given you all of the links, all of the supporting resources that you require to keep you going throughout this sad summer of spacelessness. But I'll give you one last reminder. Not from us. Just not from us. Yeah, I mean, we're going to have, the release of the images from JWST. We're going to have the launch of Starship.
SLS may have launched by the time we come back.
Yeah, August.
Yes,
at the earliest is looking good, and Starship in July. So, all right, let's get this thing started. Hello, everyone, and welcome to the Weekly Space Hangout for Wednesday, June 29th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about a new booster impact crater on the moon, a fast nova, what to see in the sky this summer, the damage of space tourism on the ozone layer, and a super Jupiter found in Gaia Data Release 3. Super Jupiter, I like that. Joining me this week, we've got Pam Hoffman. Hey, Pam.
Hi, Fraser.
Hello, Pam.
How you doing?
Good. We've got Dave Dickinson.
Okay. Good.
Hey, still here in Norfolk for now. It's the capstone launch replay on the TV in the background, if anybody is interested.
Oh, yeah, we can't see your TV.
Back there.
Yeah.
Oh, okay. Oh, it's off screen. Well, just imagine it's there.
And Dr. Leah Jenks. Hey, Leah.
Hi, Fraser. How's it going?
Good. All right, so before we get into this week's special guest, and I promise it is a very special guest, you're definitely going to want to use both of your ears to listen to this one. I want to give one final shout out for the season to our good friends at the Weekly Space Hangout crew. They are our friends, our fans, our executive producers, and they will be the place that you will congregate and wait as we go through our summer hiatus. That's right. This is the final episode of this season of the Weekly Space Hangout. I feel like we warned you. feel like we told you this was going to happen, and now that day is finally here. So this is the end of this season. The new season returns in September of 2022. So 2 months. You can make it. But if you want to hang out with some friends to keep you company and talk about space, go to the WSHcrew.space, and they will take good care of you over the summer. All right, let's get into this week's special guest. We've got Lee Feinberg. Lee, welcome to the Weekly Space Hangout.
Thank you.
Well, the question I always like to ask is, who are you and what do you do?
Well, I'm Lee Feinberg, obviously. Let's see. I am the telescope manager for the James Webb Space Telescope. I started working on it about 20 years ago.
That's amazing.
Before that, I actually
Hello, this is Pamela in the background. I am trying to figure out how to get everyone back. Please stand by. I'm not entirely sure why everyone just dropped away. I may need to blink the stream, by which I mean I definitely need to blink the stream. Working to get everything back up and working.
Passing
Thank you,
through all of its, every single, instrument coming online, a ding from a micrometeoroid, and yet here we are, just a couple of weeks away from all of that time and energy. How 20 years? I mean, it was like the Next Generation Telescope at the beginning, right? It was just a bunch of napkin sketches in the beginning. So I don't know how you could even describe it. What's it been like in sort of where you are now?
Yeah, it definitely, when I started, I really didn't know what this journey was going to be like. In fact, I actually left NASA for a year to go work for a startup company. And it turned out that I was actually abroad when 9/11 happened and realized that this company I had went to work for wasn't going to do very well in the new world after.
Trying to figure it out again. Hold on.
What I've worked on. And I thought he would want me to work on the instruments because that was my background from Hubble. And Bernie says, I have a job for you. I want you to be in charge of the telescope. And I said, the telescope? I said, I've never built a telescope. And he said, nobody has ever built a telescope like this before. And when I started my job, I got some of I guess it was like the phase 1 studies that the prime contractor teams had done, where they showed how the mirrors would unfold and how they would, and it was like, whoa, this is just another order of magnitude beyond anything we've ever done. And you go from that where it's like you just don't know what this journey is going to take you through year after year of slogging through one technical issue after another. But like you said, I mean, the last 6 months have almost been surreal for a lot of us. Launch day was definitely surreal. I mean, we never had the view that we were going to be able to see Webb in the videos with the Earth in the background, the solar array deploying. I mean, we only added those cameras like a year and a half before launch, and I don't think anybody thought we were going to get those kind of views. So, not only was it would have been surreal enough just to launch and be successful, but to actually have these like videos coming down showing you all that and showing you what the hardware looked like that you had modeled and analyzed. It's been
Yeah.
it's been quite a ride.
And it was so amazing to see it take off on the first go, which is, normally for fairly complicated missions, you're waiting for the exact perfect weather, all conditions. I was ready for days upon days of delays, and yet right on time, away it went.
The launch was flawless.
Yeah.
And Christmas Day, we were like, can they launch on Christmas Day? It's like, apparently they can.
Yeah.
Yeah.
And
it was early. If you're on the East Coast, it was pretty early too.
Yes.
And again, like, I don't think I could have pressed the button. Like, no, let's just check it one more time.
Yeah, I mean, honestly, like, because the telescope is all folded up, it really was those final tests and the final, kind of folding of it up and putting the final installations of all these release devices. All of that happened months and months before. And so, really by the time we got there, it was like, and, if I'm going to be very honest with you, we were all pretty worn down. It's been a long journey. It was a really long journey at the end. I think we were all just ready to light the fuse and let's get on with this. Kind of.
Yeah, you're capitulating. Like, that's it. We've done what we can. Let's just launch.
And just there's nothing. I think actually it was John Mather, who's the Nobel Prize winner, project scientist, but. He had some really great quotes right before launch, I think, that really helped the team. But he was like, we've done everything we can at this point, and so that's all you can do. So we kind of felt that way. Yeah.
So how is the telescope doing?
It's actually doing quite amazingly. We actually had, a little media event this morning, and I was able to share some of the performance numbers, and I'll share them with you because they're really quite remarkable. And I don't think I ever thought I would be saying this kind of stuff. But, we designed the telescope from an optical point of view, which, really what drives the science at this point is going to be, that kind of stuff, the performance. And we designed it to be what we call diffraction limited at 2 microns. And there's a good reason we chose 2 microns, actually. It actually evolved over time, even while I was on the project, because originally we were going to go for a little shorter wavelength. But, Hubble and ground telescopes can do really well up to about 1.7 microns. That's where the thermal emission from a mirror that's at room temperature really kicks in. And so we designed Webb to kind of pick up where ground telescopes and where Hubble kind of can't quite have the sensitivity anymore. And at the shortest wavelength, at 2 microns, right near that cutoff, is where we said we want perfect image quality that's only limited by the laws of physics, not by our ability to make the mirrors and align the mirrors. So that's what diffraction limited means. It means you're only limited by the physics of diffraction and not how well did we make the mirrors.
Right.
So that's what we set out
to. A platonic perfect mirror.
Yes, if we had a perfect mirror, perfect alignment, and we're only limited by, and it's fun to be on a technical thing like this, but it's what it really is it's the wavelength divided by the diameter of the primary mirror or the pupil. So it's lambda over d. That kind of defines your resolution. And nowhere in there is I didn't make the mirror right. Yeah.
I have an amateur astronomer question I've had asked, and I was like, I don't know. Are the spiky stars, is that going to be a permanent feature in the images from JWST?
Yes, it is. And that's because of the shape of the primary mirror is sort of hexagonal, and we have struts. So that's also from diffraction. Diffraction is kind of the wave property of light, electromagnetic waves, and waves, when they hit something, they diffract. They create these little waves. But that same thing is what says you can't make a star any smaller than lambda over d, wavelength over diameter, as long as you make your telescope right. Well, the bottom line is, our goal was to be diffraction limited at 2 microns all the way through the near cam, the near infrared camera shortwave channel. That's like the highest performing in the short wavelength. And today what we announced is we think we're at about diffraction limited at 1.1 micron. So that's almost a factor 2 better in image quality than what we set out to do.
And so that's that is like doubling. Is that doubling the resolution of the telescope?
It sort of is. What it really means is at the shorter wavelengths, like below 2 microns, we're not going to be limited by the mirrors and the alignment, the quote aberrations, but we're going to be only limited by the laws of physics all the way down to 1.1 micron. So it means that we're going to get a crisper image at the shorter wavelengths.
Right, but that's not necessarily going to give you wavelengths that that weren't designed in the instrument. You're not going to be able to see further.
We'll never
into the infrared.
We can't do better than the laws of physics, and we can't do better than diffraction. So we're still going to have the same resolution, for example, that we thought at 2 microns.
That's amazing.
But what goes into that is, I'll just give you a few examples because I don't think people understand how complicated this was. There's a reason it took so long. But we have lightweight mirrors. They probably suspect, but trust me, their suspicions are like an order of magnitude. Yeah, it still was way more complex than you would even think because we had to fold it up, but those mirrors have to be super lightweight. They're 10 times lighter per unit area than Hubble. I mean, if you've ever been to the Smithsonian and you've looked at the spare Hubble primary, it's like so thick out of glass. Our mirrors are these super light-weighted beryllium mirrors. Beryllium's light to begin with, but then we machine the back of them so that these little ribs are they're so thin that if you rubbed your finger on it, you literally get blood coming out of your finger. They're like a millimeter thick. Wow. That's how light-weighted it was. And the mirrors deform in the presence of gravity. So we literally, and the gravity error is quite large on the ground. So we literally had to make sure that we polish the right surface so that when you were in zero gravity, it would be correct. Plus the mirrors deform when they cool down. We cool them to, between 30 and 50 Kelvin, above absolute zero. So they deform almost as much as they deform under gravity. They deform when they cool down. So we had a process we call cryopolishing, where we would have to put the mirrors inside of a liquid nitrogen and a liquid helium shroud. The helium is inside the liquid nitrogen shroud, just to get them cold enough. And then we'd have optical equipment looking through a window that was thermally isolated that would then measure the mirrors. We'd measure how they deform as they cool down. We'd warm them back up, and then we would send the polishing hit map to the company that polished them, and they would polish the opposite. And so that when you cool down the next time, you'd get what you want.
That's
in
amazing.
The presence of gravity. So then you had to model the gravity, cryopolish them. You had to get each mirror from one to the next. We call it the radius of curvature. The curvature of one mirror to the next had to be exactly right. It is a very small tolerance we have with an actuator, but you really had to match them. You don't really think about when you make, normally you're just making a single mirror. Here we're making 18 different mirrors that all have to match their curvature. So we had to get that right. Again, measuring them at cryogenic temperatures relative to each other, which made it even more complicated. And so, all of that, and then you have all these actuators that have to move in steps that are, they're 10 nanometer steps basically. A nanometer is like a billionth of a meter, right? A fraction of a wavelength of light. They have to move in individual steps at cryogenic temperatures. There's 7 on each one. We had 132 of them. This is just on the primary mirror, the telescope. And so they all had to work and, work at these cold temperatures. And then all of that optical stuff has to work at those temperatures. And that I'm just giving you like one little slice of,
right.
I could go on and on and on about every subsystem like this.
The sun shield, the
sun shield.
The instruments, the coronagraph.
The instruments, everything was this complicated. And so
and there's no fixing it either, like Hubble.
Right. There's no fixing. Although, you
can't go out and fix it.
No, we can't fix it, but the one thing we have is we have what we call correctability, which means that primary mirror with all those little actuators, we can actually, if we had I got asked this a lot, like if we had the equivalent problem that Hubble had, the spherical aberration, we actually wrote a paper on this, and you can actually do a pretty good job of correcting it using our actuators. There's enough degrees of freedom to approximate that shape pretty well. And that's actually helpful. It's helpful because the one thing that number, our 1.1 micron diffraction limited, doesn't include is how things change over time, for example. And you mentioned micrometeorites, which are one of the things that occasionally happen. by having adjustability, when you get little things that change, a mirror shape, you can move the mirrors around to more optimize where they are, and that removes, a lot of those effects. So having that active level of control was very helpful. And we do expect over time. Go ahead.
I was going to say, even if like the mirrors like continue to cool down, you may get additional warping, and then you can correct for that over time.
Yeah, I mean, at this point, the mirrors are totally stable temperature-wise, so we don't expect any more warping, if you will, or deformation. So we think they're kind of in a static state, but over a long period of time, over many years, you'll get little micrometeoroids hitting them. That's the main effect we get. That's kind of a lifetime effect. We also, the sun shield itself will get hit by micrometeoroids and will degrade a little bit on the thermal side, and so we've accounted for that in our stability numbers. The other number I shared this morning was our stability. Our stability is insane. We in our models we thought we'd be thermally stable over, say, the primary mirror to 17 nanometers, and we are thermally stable to 17 nanometers, which nanometer is a really small number. That was really hard. That was maybe, from a telescope point of view, the hardest thing we had to do was make this humongous primary mirror stable. So, and what that means is, as we slew around the sky, things change temperature, and we can't have one mirror to the next moving around, tipping and tilting by more than 17 nanometers across the whole primary mirror. And what's unique about Webb is that, in a normal, like take Hubble, for example. Hubble is just a single monolithic mirror, which, by the way, they temperature control. They have heaters. And so as it slews around the sky, they just kind of keep it at a constant temperature. And it's just that piece of glass has to be, have a very low coefficient of thermal expansion. And that's how you design Hubble. For Webb, because the mirrors are, separated, they're connected by a structure behind them that's made out of composite. So that composite kind of acts like part of the mirror in the sense that it has to be stable, just like the mirror. So we had to design the 6.5 meter composite that has to be stable to 17 nanometers. And that's what was so hard. And that was just to figure out how to test that. We had to invent technology, let alone invent the technology for the composite structure itself. We kind of designed a new cryogenic laminate. So, these are little subtleties you don't hear much about, but that's what we've been working on all these years.
So, at this point, again, we are around 2 weeks away from seeing those first images. So what went into actually, I'm assuming, has the data been gathered already for those first images that are going to be released?
Some of it has. There's still some to go. They talked a little bit about that this morning. So I'm somewhat up on where they are. I personally wasn't directly part of choosing those images. There's a small team of people, but they have taken a bunch of the data at this point. And they're smiling a lot.
Yeah, just wandering around in a stupor, staring at a picture. That does sound amazing. So I guess, what are your hopes at this point for, I think now that you've got this level of stability, you've got this level of resolution that's coming in, the clock is ticking for the lifetime of the telescope. What are some of the big observations, some of the big questions about the universe that you would love to see some really serious progress made on?
Well, let's see. I think the two things they announced this morning that are going to be part of our very first, early release observations in 2 weeks are, they're teasers, but they really are, they get at like the most fundamental things about James Webb, which is, number one was, it was designed to see the early universe. It really came out of after, we repaired Hubble. They took the Hubble Deep Field, right? And they're looking at this incredible image and data of, galaxies farther and farther back in time, but, they could only get to when the universe was about 1 billion years old. And, they realized that if you really want to go farther back in time, you actually have to look in the infrared, because the universe expanded, this huge expansion and acceleration that stretches the light into the infrared that starts, starlight is visible, right? We see the sun with our eyes, but when the mesh of space-time gets stretched, and light is traveling through that mesh, I call it a mesh, and the mesh gets stretched, the light gets stretched into the infrared. And that's why, you really have to look in the infrared to look farther and farther back in time. And you need a lot of sensitivity because these are dim objects. And so that's really, to me, that's right at the core, and I really think, we are going to see the, beginnings of at least the universe once, there was light that could be detected. There was this very early phase, right, with the Big Bang and all that. And there was no photons, coming at us from that phase. But, maybe 100 to a couple 100 million years after the Big Bang, they believe, after this process called reionization, that the first stars and galaxies formed. And there's black holes, and what are the role of black holes? Understanding that early universe, I think that, to me, is why Webb was designed the way it was. It's why it had to be so big and so cold and so sensitive.
Yeah. I mean, it is really interesting. Like those images. Sorry, with Hubble, even the ones that it's using, say, gravitational lensing to see a galaxy that's seen just say 500 million years after the Big Bang, it's still only able to see things in the wavelengths that it can perceive. It's that shifting into the infrared that will show all of those galaxies that were right in front of Hubble all this time, but it just wasn't capable of even imaging them. And now we will.
Yes. And, as you saw when we released our first alignment image, it's like the thing that really gets you when you take data with Webb is, holy cow, the universe is just full of these infrared galaxies. Like, we didn't, I'm an engineer. We've all been spending years and years planning how we were going to align Webb with a star. And we use these stars and we aligned it and we got this final image, and, you kind of are envisioning in your mind that you're going to have this nice tight looking star with the diffraction spikes we talked about earlier, because it's got this certain shape with the struts. And the picture is full of galaxies, spiral galaxies, elliptical galaxies. And it was like, oh my God, I never even thought about that. Like, just how many galaxies. And the one we released, it was like a 20-minute engineering image, just to kind of evaluate that things were reasonably stable and then to show that we were properly aligned. And it was like this huge number of galaxies popped out. We were just floored, So it just gives you a sense of, that's what the infrared universe looks like. Yeah. When we start doing these deep fields, you can. And
you had a second thing that you were looking forward to.
Yeah, so the second thing, we were just spending a lot of time on galaxies because they're so interesting.
Yeah, I know.
But the second thing, which really I'm confident is just going to blow people away, is the exoplanet transits. So as an exoplanet passes in front of a star, the light dips, famously, right? But what's amazing about JWST is that when that happens, we can actually, when that planet passes in front of the star, we're going to be taking spectra. We're going to be looking at, which wavelengths get absorbed. And from that spectra, you can determine what the composition of that atmosphere is. And infrared is the ideal wavelengths to look for water and to look for methane and to look for carbon dioxide. Like, a lot of interesting, things that are potentially, things that we care about for looking for planets that could be habitable, for example. They don't think that it's likely that JWST will find signatures of life, just because the types of stars that we can do this on are typically not the kind of stars that we think are, like the sun, like a G star, for example. They're not those kind of stars.
Well, we always argue about it even on Mars, and it's right there. And Venus, right?
Yeah,
like phosphine on Venus. So I can imagine it's going to be inconclusive for a while when you're looking at 100 light years away.
You probably know that there's even a whole nother telescope that's being proposed as the follow-on to Webb that the National Academy recommended, that's more focused on that big question of biosignatures and looking for life. But the transit work from Webb, I mean, at a minimum, it's just going to give us this whole catalog of, could imagine potentially hundreds of exoplanets where we know their atmosphere of each one, and how much could be learned from that. And, and there are details that you learn from doing this, and the pressures and the way the planets formed. I think it's going to really I think it'll be
Yeah.
as powerful. And I'm just giving you two examples, right? This is true for many different areas, but you asked me, I think those two areas, the transit one, I will tell you that they during this commissioning phase, they do some rehearsing of, I wouldn't call it rehearsing. It's almost like calibrations. And I remember they did the very first, very simple version of a transit, where they looked at something that's not very interesting, but everybody's jaw just dropped. It was so powerful. So that one, I'm just so confident it's going to be amazing. But there's going to be a lot of
sounds
great
great.
stuff.
Yeah, I mean, we're running out of time here. And I just know, it's going to be doing work inside the solar system. It's going to be looking at the core of the Milky Way. It's going to be looking into star-forming regions. There's just so many places that this telescope is going to change our understanding. Well, Lee, congratulations on 20 years of nursing this telescope into existence and into its final home. And now here we are, just a couple of short weeks away from the rest of the world being able to share in all of that data as it comes together. Congratulations to you and the rest of the team.
Thank you so much.
And we cannot wait to see. It's going to be a wonderful decade of science and knowledge. What is the best way for people to keep track of things? What's the best way for people to keep track of what you're doing as they?
I think most people go to the website, jwst.nasa.gov works, or nasa.gov/JWST. If you go to our website, they are really good about keeping it up to date, and so that's probably the easiest thing to do. And there's blogs. There's a weekly
blog
blog
is so good.
Yeah. I've written a couple of those. They're great though. They really, and I learn a lot from them because somebody else writes one and I read it and I'm like, oh, that's interesting. So
yeah. They're quite technical, but also very accessible, and they really help you understand the kinds of questions that you've got about it. So all the people that are working on the blogs are great. Well, again, thank you so much. Good. And when you launch your next telescope, will you come back and tell us about it?
Yeah, hopefully it'll be 10 years, though. I'm going to go for 10 years on the next one. How
that sounds great.
Okay.
Yeah, we'll talk about Lubex in 10 years.
Lubex in 10 years. You got it.
All right. Sounds good. All right. Thank you so much.
Nice to meet everyone. Thank you.
Bye. Wow.
Yeah, wow.
That's amazing. I'm so excited to see these images.
I know, me too. We begged him to share before the show, but apparently he wasn't allowed to.
I know, just a little sneak peek.
Come on, we won't tell anybody.
All good movies have teasers, right?
Nancy Graziano, you are the best. Just the best for organizing that. That was amazing. I feel bad. I know people listening to this interview, they're gonna be like, Fraser's cutting in. Fraser's let him answer the question, Fraser. That's one of the longest interviews we've ever done. We have a bunch of news to get to, and I just needed to sort of keep the conversation rolling. I apologize, but wow. Anyway, we need more time. Can we make this show twice as long? Would that be all right with everybody? All right, Dave. Let's talk about the booster impact on the moon. And now you've got 4 minutes.
This was, it's pretty simple. The booster hit the moon. But on March 4th, there was actually late 2021, there was an object that was identified in Earth orbit that was obviously a piece of space junk that they were looking at. That at first we thought it was from SpaceX, from the Discover mission that was launched in 2015. But it was later identified, of course, there's an image from the Virtual Telescope project. They actually got it. You can see it tumbling there too, and it's flashing. This object hit the moon on the lunar far side on March 4th, and it's been pretty much identified as the Chang'e 5. This mission's kind of been forgotten about. Chang'e 5 T1, which was the test, re-entry test for the China's full sample return mission that they did in last year, I believe it was. But this booster hit, and the Lunar Reconnaissance Orbiter, NASA's LRO mission, actually managed to identify, you can see it there in the before and after, a strange double crater. And it's kind of interesting that other impacts have been found, like from Saturn boosters and things. We've never seen one do a double crater hit like that before. So there's some thinking out there that really a booster is the weight is toward the motor end of the booster, and it's essentially a giant empty aluminum can that's it's been emptied out of its fuel. So either this booster had broken up, or maybe it tumbled when it hit, or there was some odd reason that it did a double hit like that. And China, incidentally, has never admitted that this was theirs, but they're kind of enigmatic about as far as what they're doing in space. But this was from a Long March 4C rocket, I believe, that they launched. So it was kind of interesting. I was kind of hoping it would have been SpaceX's, because then at least we could say, I think initially in the article, that SpaceX did reach the moon, just not the way they intended to reach the moon.
Right. They litho-braked onto the moon with a spacecraft. Yeah.
Yeah. So I thought it would have a little distinction there to say that was the first time a private, because the first thing you do is early on the space program, the first thing before you soft land or orbit or anything is you end up usually just hitting the object. So, which is what we did, I think 1959, Luna 2 was the first thing that just hit the moon, and the very first Ranger missions, they all hit the moon. So there's still boosters hitting the moon even today.
Right. Yeah, the moon is a tricky place to actually even remain in orbit. That it's the the interactions with the Earth, the bumpy gravitational field of the moon, things can't stay in orbit for very long. I'm surprised LRO's been around for so long. Very cool.
Yeah, LRO's been a great workhorse.
Yeah. All right, Leah, let's talk about, of course, rockets are going to wreck the environment.
Yes, unfortunately. So this is a paper that came out last month, and there's been some press about it this month. From researchers from University College London, Cambridge, and MIT. And basically, they were looking at the effects of rockets and space tourism on the ozone layer. So as I assume we all know, there's a big hole in the ozone layer from carbon in the atmosphere that was discovered in the 90s. And since then, there's been the Montreal Agreement or Accord to try to get that kind of back down and rebuild the ozone layer, which as of 2019, I think it's the hole was the smallest it's ever been. So the ozone layer was starting to heal itself. And then now all of a sudden, Elon Musk and Jeff Bezos and Richard Branson and all their rockets are potentially going to throw a wrench in that. So basically what this study looked at was all the space launches from 2019. So I think there were, 103 different launches, and they looked at the different types of fuels that all of these rockets were using. And then they also looked at potential reusable rockets and space debris re-entering the atmosphere, and then used a climate model to predict the effects that this would have on the ozone. And what they found was a little bit concerning. So assuming kind of far down the road that I think Virgin Galactic was saying that they're at some point going to have daily tourism space launches, and SpaceX and Blue Origin are saying maybe weekly. So using that kind of parameter and modeling the fuel and everything like that, they found that the kind of soot from the fuel that gets deposited into the upper atmosphere, into the ozone, is actually holds on to heat. I think the number is 500 times. It's 500 times more efficient at holding on to heat than all of the other soot pollutants from commercial flights and other surface pollution combined. So right now, this is obviously, it's a small effect because there aren't actually that many of these flights happening. But it seems like in the very near future, this is going to really ramp up. And so these researchers basically recommend that this be pretty highly regulated to, not lose all the progress we've made on the ozone and not make it worse.
Yeah, so the problem that you've got is that they're putting this material up into the troposphere.
Exactly, it's going directly into the upper atmosphere. There's nothing else.
Yeah, and there's no other way that human activity can put material up into this level. And I think the estimate that I saw was essentially a 10x factor in current space flight crosses that line. and you're now doing additional damage. And you're talking about the space tourism is definitely one possibility, but I mean, even just an increased launch cadence of
sure.
Starlinks and scientific satellites and space tourism and starships on their way to Mars, carrying 1,000 starships launching to Mars. Like that plan of sending 1,000 starships to Mars every 2 years to build the Mars colony, that alone would ruin the ozone layer, just like that.
Yeah. And I think there's like an interesting kind of, trade you have to make, right? Where to some extent, like we care about space flight and space travel and innovation. And so it's important. But like at what point does it become kind of too much, and how is that going to be regulated? And I think that's a super important and interesting and difficult question to get answered over the next couple of years. But you make a great point that all of these other even non-commercial launches as well will definitely have that impact.
Yeah. So I mean, like, there's no free lunch.
That's unfortunate.
All right, thanks, Leah. Yeah, it really is. I was sort of looking forward to this Star Trek future, but now, I guess when we get warp drives and dilithium crystals, then I wonder about like what about a oxygen hydrogen rocket as opposed to a methane one, like the SLS. But I guess, I mean, it's solid rocket boosters are blasting out. I don't know what they're shooting out, but if you had a pure hydrogen oxygen, then you're dumping water into the troposphere. Is that okay? Anyway.
Yeah, and the rubber stuff is really nasty.
Yeah, exactly. All right. Yeah. Thanks. All right, Pam, tell us what to see in space.
Sure. Summer is still going to be really good for early birds, but things are going to shift a little bit into the more late night. And I think eventually we'll get some planets in the evenings again. And of course, there's still some strings of them. They're going to kind of break up a little bit. They're not going to be quite as elegant and in order, all that sort of thing. Mars is going to get brighter this summer. And I actually learned something. You can see Uranus with binoculars. It's going to be kind of close to Mars in August, and it'll be a good contrast because it's kind of green. So,
but it's going to be
general,
breaking the rules.
Showers.
Right, it's going to be not in line with the rest of the planets, right?
Oh, it's been breaking the rules the whole time, I think.
Yeah.
We've got 2 meteor showers to look forward to this summer, and I found a couple cool activities, 2 globe at night projects, and I think there's kind of 12 conjunctions that are really worth talking about. No eclipses, though. I'm so sorry. We're going to have to wait until the fall.
Yeah. So what are the meteor showers?
Yeah, we've got the Delta Aquarid meteor showers, and that's the date range is basically July 12th through August the 23rd. The kind of peak, though, should be around July 29th, 30th, after midnight from Aquarius. Really low numbers, though, 10 to 20 per hour, and this is from 96p/Machholz. Moon's good, though. It's going to be 2 days after the new moon. The moon will be very, very, very thin, and it'll set really quickly. August is going to have the Perseid meteor showers, and this one going to have a big moon, unfortunately.
Yeah, it's going to suck.
The date range is 7. Yeah, sorry. I mean, and this one's got like the 50 to 90 per hour, and that's a big one that everybody talks about on the news. July 17th to August 26th, though, and you can see them at other times, but the peak, they're talking the 12th and 13th after midnight again, radiating from Perseus. This is going to have a full moon on August 11th, however, so it's still pretty big by the 12th. Some cool events, and I just found this one recently. This is Science is Cool. It's a worldwide virtual unconference for cool teachers. It's going to be August 5th, 9 a.m. to 4 p.m. Pacific time. So Pacific time, remember that part. We've got the, and I found this from my friend on Facebook, and I thought, oh, this is really cool. Scavenger hunt. I've tried to look for more, but I haven't been able to find anything. So if you know anything about it, please let us know. This is July 1st through August 7th. A little bit of time. It did kind of turn into this other cool thing, though. The celebration of Kennedy Space Center's Diamond anniversary. Maybe what's going to happen is on this July 1st event they have, they'll kick off the scavenger hunt. I'm hoping we're going to learn more about that very, very soon. I will have my shows every Friday through the summer. July 1st through the 2nd is this particular celebration. All right, so like I said, we have 2 Globe at Night projects, and this is real citizen science. You can definitely help, and this is anybody anywhere in the world. We've got some Southern Hemisphere and Northern Hemisphere targets. So July 19th through 28th and August 18th through 27th. We have, of course, the first one is Scorpius and Hercules. And again, Hercules and Sagittarius for the second set. And each project lasts 10 days. The idea is you go out, you take pictures, and they outline it here too, and report back to the site. This is actually very, very useful for the folks to understand what's going on with things like light pollution. And it could be a pretty busy summer. We've got July 4th, which Earth is at aphelion. It's the farthest from the sun, weirdly, because, of course, in the Northern Hemisphere, it's hotter. In the United States, it's Independence Day that day. The first quarter moon is July 6th. And then there's a full blue moon on July 13th. On the 15th of July, Saturn and the moon are in conjunction. That should be pretty brilliant. The 18th is Jupiter and the moon, also pretty neat. July 20th, and that's actually a very auspicious date because that's the landing of Apollo 11 on the moon. Last quarter moon, July 21st, Mars and the moon are in conjunction. The 26th, Venus and the moon are in conjunction. And a lot of the stuff is still happening in the morning for you early birds. The 28th is a new moon. New moons are always good for observing. The 29th is Mercury and the moon are in conjunction. And on August the 5th, we have the first quarter moon. So I'm going to cover the whole summer because we're going to be gone until September. August the 11th is the full Sturgeon moon. That one's called Sturgeon. Also, Saturn and the moon are in conjunction. Yeah, some of these are really beautiful with like Saturn and Mars, and it's just terrific. On the 14th, Saturn is at opposition. Opposition's always the time that it's kind of the best to get photos of these because kind of the closest Earth orbits every year will kind of be opposite one of the planets. On the 15th, Jupiter and the moon are in conjunction. And on August 19th, last quarter moon, Mars and the moon are in conjunction. And that one should be really gorgeous because Mars is getting brighter and brighter. And I think we're going to probably see like launches figured out soon, right? Because every couple of years we have launches to Mars.
I don't think we have any this window because ExoMars Rosalind Franklin was going to go. And because of the Ukraine war, that got screwed. Well, it's pushed back. They're still trying to do it. So I think
I don't think
we talked about this.
I don't think the Chinese have anything. I don't think anyone else has a mission going to Mars this window.
I think early on when we had when the Ukraine war just started and we talked about it, that this is the first Mars window in quite some time that there hasn't been a launch.
Wow.
There's not going to be.
That's unfortunate because we do a lot of really good science. And it only comes around a couple times every couple years that we can kind of launch.
We had managed to send.
It's really unfortunate.
Last window 3 went UAE, China, and Perseverance. Yeah. So it's kind of sad that we're missing a Mars window now. Too many lows on Earth right now.
Yeah.
Got it. Okay. Yeah, I hadn't heard anything, and that's probably why. Yeah, Fraser.
Oh, I'm sorry.
You have something?
Were you done? Were you wrapped up?
You made. I got a few more.
Okay. All right. We're just getting low on time, so.
Got it. All right, let's wrap it up here. Okay, so there's a bunch of conjunctions this summer and into September. Check it out. Go outside. Look up.
There you go. Go outside. Look up. Enjoy.
Good advice.
Yeah.
It's
Dave.
always the.
Thanks, fam.
Yeah.
All right, Dave. Let's talk about the Fast Nova.
Yeah, last year, I believe it was in March 2021, there was a nova, a galactic nova, as opposed to an extragalactic supernova. And there was a nova in our galaxy that flirted with naked eye visibility. It hit about 6 magnitude. Now, these aren't uncommon. And as you can see, the artist conception up there, a nova is basically you have a white dwarf siphoning off material from a main sequence star that's compressing on the my astrophysics is being very succinct on this, but the material is being compressed on the surface of the white dwarf. Nuclear fusion occurs and it flares up. Occasionally, there's what's called recurrent novae, like Scorpii actually just did flare. That's another one. But this one was about 15,000 light years distant. We see one of these every few years, and sometimes they get up toward. We had one in Delphinus about a decade ago that got up to first magnitude, and that was kind of cool because you could just walk out and see it. And the constellation actually looked different because nova, it's a new star, and it just appeared there. But most novae go for about a week or so before fading out of visibility. But this one was very strange, this Nova Hercules 2021, in that it flared and faded within a day. And this broke the record for the fastest fade out. It faded by about 5 magnitudes, which is about 100-fold in 24 hours. And that broke the record by about, I think, 3 days was the fastest they had seen one fade out that much in 1992. Now, there's a lot of discussion about exactly why this is. They're not sure if it has something to do with the geometry of the system. Again, it's 15,000 light years away, so we don't actually see the two white dwarfs in the main sequence stars as separate. It's back down to like 20th magnitude now, so it's very faint. But there is an oscillation in there that they thought was very curious that was by about 500 seconds long, which is under 10 minutes. So they think this oscillation has something either to do with the orbital period of the main sequence star around the white dwarf, which would be they would be in a very tight embrace if that's true, that's actually doing something with the geometry of the system there. And this oscillation was visible across visible light and X-rays. They examined it mostly with the spectrographs on the Large Binocular Telescope at Mount Graham. But they actually got some X-ray observations from some various missions on this as well. So it's intriguing that it's a record holder, and it's interesting. I was talking to the researcher about the elements in the production that this puts into novae, and explosions are putting more. The fission process is happening, seeding the cosmos with more heavier elements, metals. Metal in astronomy, of course, being anything that's not hydrogen and helium. But he also talked about lithium, and I kind of tickled my brain about, I know there's a cosmological problem with what they call the lithium problem out there, as far as the amount of lithium that's in the current universe, and even like what we see in our sun, which is very metal rich, is discordant versus what cosmological models like the Big Bang would predict how much primordial lithium there should be. And he was saying, they think that a galactic novae like this are prime seeders of lithium actually in there. So I thought that was kind of intriguing that this may go toward putting a piece of the puzzle in there as far as I just found out about this reading. It was either something I wrote or something I read a few months ago about there is what's known as the cosmological lithium problem out there in astrophysics. So I thought it was intriguing that there was a tie-in. I asked the researcher that. It's like, does this tie in? He's like, this could be a piece to that puzzle, actually.
It's interesting, like a piece, like just like with the missing matter in the universe, like just the regular baryonic matter, it's not one thing. They're finding it in intergalactic gas. They're finding it in various different places, bit by bit by bit, and they've been able to add them all up together. And same thing with the lithium problem. It's, when you think about stars, they hold on to their material quite well, and so it's sort of a mystery how we have all the heavier elements that are here in the Earth. We're
not made of the most common things out there.
Carbon, gold, nitrogen, all of that, right? And and we're finding sources of these things, colliding neutron stars. And now, like,
I believe that's the most common source of gold, isn't it? Is neutron star mergers. Which is really blows my mind to think that.
But it had never occurred to me that novae are a source of nuclear synthesis. That they're producing heavier elements and blasting them out with each time they explode. And my assumption had always been that when when you have a novae, you get this explosion, and then it just keeps happening and keeps adding a little bit more, and eventually you cross the 1.4 times the mass of the sun, and then the thing just detonates as a type 1A.
They can mature into supernovae,
right? But now it looks like actually they get a little lighter every time they have a nova, because they're actually blasting a little of the underlying material as well. So a star that is going regularly nova probably can't go supernova. which was really interesting to me. Anyway,
the recurrent nova are actually pretty rare. I think there's half a dozen or so known. T Pyxidus is another famous one that amateurs are the ones that are monitoring these, by the way, and usually they are the first ones putting up the flag on when these kind of stars are reaching above 10th magnitude or so.
Yeah, got another story for us. A super duper Jupiter.
Yes, so super quick, but there's a super Jupiter, say that 3 times fast, in the new Gaia data release 3 catalog. So the Gaia satellite from the European Space Agency is mapping out stars in the Milky Way. And like JWST is going to is going to have many, many applications to like cosmology and astronomy and exoplanets. And they just released their 3rd data release. And in the paper accompanying that, they gave a little bit of a sneak peek of some of the things that are currently in the data. And one of those is this observation of a hot Jupiter-like planet orbiting a white dwarf. And this is interesting because this is a notoriously difficult thing to actually observe. Because obviously white dwarfs are very faint, they're very small, they're not really doing all that much. And so to have an actual observation of a Jupiter-like object, I think it's 9 Jupiter masses, so super Jupiter, around this white dwarf is a really impressive observation. And I think they also flagged like 4 other potential candidates that aren't just as sure yet. We need more observations. And this is actually the 3rd white dwarf white dwarf hot Jupiter exoplanet system actually ever found. So this is a pretty rare thing. But hopefully with the new data and over the next, I think 5 years, they have plans to release a lot more. We'll get to see more of these systems and learn more about how they form and their dynamics, because it's also a really interesting test of a binary system, because in this case, the planet is massive enough to have an actual gravitational effect on the white dwarf, so we can learn about binary systems in general too. So cool observation and pointing to exciting things to come.
What's amazing about Gaia is that it can do all 3 types of planetary observations. It can do a radial velocity measurement, measuring how the white dwarf, I guess, would be moving towards and away from us. It can measure a transit, because it actually has a very sensitive photometer on it as well. And it can also discover planets the way none other can, which is to use astrometry and actually see these stars making little circles in the sky as their planet is yanking them around. Do you know which of those techniques they found this planet with?
Yeah, so this one was from the astrometry. So they were tracking the orbit of this star and saw that there was like a little wobble, and that wobble in the orbit was too small to be another like binary star, and they could figure out the mass of it, and so they have the analysis to show that it's one of these hot Jupiter.
It's amazing to think that when you have like the radial velocity method or the transit method, you're only seeing like 1% of the stars that are lined up perfectly. So we get that, we can see them coming towards us and away from us, or see the planet passing in front. But with astrometry, then you get all the rest of the orientations.
Right.
And so it, in theory, is the technology that would get us the 99% of the planets that we can't see any other way. And it's in there in the data, and it's just a matter of with each subsequent Gaia data release, we'll just get more and more and more of these things. So this is a really exciting. It's sort of in my head. I got a chance to interview one of the people on the Gaia team focusing on white dwarfs, and so this was the object he was really excited about, was this exoplanet orbiting around a white dwarf. But even like to think about that you've got a dead star with a planet orbiting around it, like what happened? What was the story? What was the original star, and where did it migrate? Yeah, really interesting stuff. All right, well, that's it. We've reached the end of our hour. We made it, and this will go down in history as an amazing episode for the incredible interview. thank you, everyone, for joining us for another season of the Weekly Space Hangout. We really appreciate it. Thanks, everyone, watching us both on YouTube and on Twitch. Thanks to all the moderators working. And thanks to Nancy Graziano. Like a special 100% mega shout out down to 1.1 microns of resolution. Nancy, we could not do the show without you. We really appreciate all of your mad volunteer organizing skills, and it's been an absolute pleasure to work with you for another year. Thanks to Pamela for engineering behind the scenes. Thanks to all of my co-hosts and our special guest, and we will see all of you in September. So we won't be here next week.
We'll have launched by then.
Exactly. After
we'll have
Starship, after SLS, and after James Webb.
Starship will be in orbit. We'll have orbited.
Yeah, we'll see you then. Thank you, everyone. We'll see you in 2 months.
Have a great summer.